Hello, my name is Adi and I'm going to be presenting a C3d tutorial on how to set up a pool fire with an immersed object, and in this case it'll be an airplane as you see in the image. Let me go back to the beginning of the video and I will describe what's going on here. What you see is an airplane with a hole in the ground, which is basically a diesel fuel fire. And let me play the video. And what happens is that there's a wind in the crosswind direction here. The pool fire starts up. It starts engulfing the airplane, and the wind is blowing across the airplane and causing it to heat up and melt the skin. As the image rotates, you can see how engulfed the airplane is. Now, on the second rotation, I actually turn off the evaporation of the pool to allow the remaining vapors to go ahead and dissipate and burn off whatever's remaining. And as the plane comes around, there's a little bit of residual fire going on. It's almost gone. You'll see that it has heated the skin up and melted holes in it. In this last rotation, it actually gives a close-up of the damage incurred by the aircraft, and all this is going to be taken care of in the simulation that I'm going to show. As you can see, there was a considerable amount of damage, and I think that pretty much covers the what we're going to go over. So in this particular tutorial, I'm going to be taking a complex object like the one you're looking at here, an airplane, that you would not be able to build with the C3d solid modeler, because its primitives are fairly simple: cylinders, spheres, and so on. But this is a STL object that I managed to download off the web, and you can see it's a very good representation of an aircraft. If you actually get a file that you have imported, the first thing you need to know is what the scale is. And this is ParaView. What I'm going to do is take the ruler and measure the wingspan. Whoops. I didn't want to do that. Let me try it again. Okay. And click on apply, and it tells you how long it is. It's 2,900, say 3,000 of whatever units the STL file came in. I'm going to assume it's centimeters. So multiply this by 0.01, you would get 29 meters, which it's kind of like 100 feet, of that order. It may be wrong, but it doesn't matter. This is just a demonstration calculation. The other thing that I want to point out is you want to figure out where to put the pool. I'm going to put it right here, so I'll click on to get that point. It'll be at an X value of, well, if we use centimeters, it'll be -1 meter, a Y value of 5 meters. Okay, so that'll be the center of the pool. And the last thing we want to get is how far above the ground this is. So I'll click on this point and get that. And the Z location looks like it's, if it's centimeters, it's a -1 meter. So it'll have to be raised. And those are parameters that you have to keep in mind when running the C3d GUI. Okay, so the next step is to bring up the C3d GUI, and what we want to do is build a jet fuel fire. So we'll click on combustion model, and jet fuel, the closest fuel is dodecane, which is very close to jet fuel. So now we want to modify that existing file. And as before, you'll have a single time step. The equations are all set up. The fire model. Let me bring up the chemical reactions. You can see dodecane is fairly complex. There's a lot of chemical reactions going on. So, and we'll leave those as they are. They're set up nicely. So Now we want to bring in some properties. As before, we just have insulator. But we do want to add some materials. And basically let's bring in aluminum just for the skin. I think that's all we're going to model is just the skin for this particular calculation. And again, it comes in with an emissivity of 0. So I'm going to set it to be 1. The actual emissivity of aluminum is around 0.1. But that if I use 0.1, that means that the calculation has to run at least 10 times longer to get to the same temperature. So if we make it 1, it's going to heat up 10 times faster than it really would, but we'll just keep that in mind. I'm going to set the runtime for this simulation to be 20 seconds. So it'll be kind of like a 200 second run if we were to do it in real life, or actually simulating the actual aircraft. So the emissivity is set to 1, so we're okay at this point. Now we're going to have to bring in some initial fluids to get this project started. We have air. Let's check that out. The air has a mass fraction oxygen of 0.233, and that is good. We'll leave it at 300 Kelvin, 1 atmosphere. That's okay. And for dodecane, it's a mass fraction of 1, which is what we want to use for the vapor that we're going to use to fill the pool. We're also going to use that in the boundary conditions. Fluid temperature, let's bring that in at 350 Kelvin. And 0 velocity is fine. It'll pick up speed as the wind blows across. Okay, so now we've got our initial fluids and so on. So the next thing we want to do is to set up the geometry. We'll bring up the geometry. The first thing we want to do is set up the computational domain. It'll be air, as you see here, but we want the STL object to fit inside there. So based upon the measurements that were made before, we're going to go in the X direction minus 18 to 15. In the Y direction, we'll go from minus 18 to 18. And in the Z direction, we're going to want to include a ground. We'll go in the negative from minus 0.1 to 20. And that is a good domain that will contain the entire aircraft as well as the pool fire. The next thing we want to do is to add the airplane. And that will be an STL graphics file. There are 3 types of STL file. There's an ASCII file, a binary file, which is the default, and that will map it to the Cartesian grid. But if we select STL graphics file, that's also a binary file, but it will keep the original STL polygons so that it looks exactly as it did in ParaView. We'll call this airplane. Oh, wait. The name has to be the name of the STL file, which is airplane.stl. Now, you got to give it some coordinates if you want to shift it. So the coordinates will be no X shift, no Y shift, but we're going to shift it up 2 meters because as you recall, the bottom of the aircraft was below ground. And the scale factor is going to be 0.01. And it's going to be, air is fine for the fluid. It's going to be made of insulator. We're going to map that to aluminum in the subgrid so that we can have it receive real properties, have a correct skin thickness, and so on. If we don't map it to a subgrid, then the thickness of the skin will be the cell size, which is a little bit too large. So that's it for the airplane. Next thing we want to do is create a ground surface. That's rectangular. We'll call this ground. Ground. Okay, it'll have the same dimensions as the domain in the x and y, so it's minus 18 to 15, minus 18 to 18, and it goes from the bottom of the z domain, which is minus 0.01 to 0, so that it is in the negative, and that will be made of, we'll just make that insulator for now. It doesn't matter, we're not going to map that to a subgrid. Oh, actually, it probably ought to be made of something else now that I think of it. Let's go in there. We'll make it, because when we try to map the airplane, it's going to grab the ground as well. We don't want it to do that. Well, let's just say it's going to be made of aluminum. And that's fine. It's not going to affect the airplane calculation. The next thing we want to do is cut a hole in that ground surface. So we'll call this hole. This is for the pool. It'll be at, let's see, it's going to be at -2, 5. Whoops, this has got to be a cylinder. That's why I was confused there. Okay, it starts at -0.1 and it ends at 0. So now that cuts a hole in the pool. And we want to fill that with dodecane vapor so that it burns. And the radius of the pool is going to be 4 meters. Okay, that covers that. Next, well, I think we're done with all the geometry. We might want to change the ground surface to be something else, but we'll leave it aluminum for now. Okay, let's save this data. What we want to do is go to, I've got a directory set up. We'll go in here, demo. We're going to call it C3d INP. That's an old file. It'll write over the old one. Okay. I just realized I had cut the cylinder hole for the pool in the wrong direction. We don't want an X cylinder. We want a Z cylinder so that it cuts the ground in the proper direction. So we'll click on OK because we're done with geometry. Before setting up the boundary conditions, because we want to set up a wind and so on, I want to actually look at the object. So I'll go in here and mesh it according to the geometry. I'll just put in a default of, say, 50 cells and let it select the geometry. It's going to be a fixed Cartesian grid, but I kind of want to have it mapped correctly just so I can view it. We can go in here and refine this mesh later. I'll use 50 cells in all 3 directions. Okay, now it's meshed up for viewing. I'll save that data. It's under airplane demo. And then I'm going to go ahead and run it for one time step. I've already saved it, but it wants me to save it again. Well, that's one thing that we could turn off, the duplicate surface polygons. Since I've run this problem before, I know that there are no duplicates, and I want to turn that off because you can see it takes up a lot of time, which is no reason to have us wait. Okay, so it ran. Let's view the mesh. Okay, there it is. Let me turn off the grid so you can see the hole. There's the hole for the pool. You can see it set underneath the wing. There's the ground surface. And let me turn on the grid again. And you can see that the domain, it's above the ground in a nice location. And it covers the entire aircraft. So the what we have here is pretty good. Now we want to have a wind blowing in this direction, which is negative y. So we want it to blow from y max toward y min, and we'll blow it at 3 meters per second. Okay, now that we know which direction we want the wind to blow, we're going to go in and set up the boundary conditions. The first one is, these are the default conditions that came with the input file. We have species, oxygen fraction is 0.233, that's mass fraction. So it's set to air. And this is zero flow and a 300 Kelvin temperature. The next thing we want to do is add a wind boundary condition to all faces. And that is a momentum condition, wind, x component 0, y component will be negative 3. It's flowing from y max to y min, z component 0. Next, we want to add hydrostatic so that it can flow out everywhere. I believe that is also combined. Yes, here it is, hydrostatic, and we give it a temperature of 350. Okay, now this overwrote the normal velocities of all these other momentum boundary conditions for the wind, but it did not overwrite the crosswind velocity. And that's why we wanted to do it in this order. However, it did overwrite the normal condition for the inflowing wind. So now we want to apply the wind again, but only on the y max boundary. Momentum, wind, 0, -3, and 0. Okay, so now we have crosswind on all the boundaries from this hydrostatic, this combination of boundary conditions, and we have a normal inflow on this one. Now we need to set up the inflow of the dodecane gas at the pool. So that will be on the Z min boundary. It'll be it's combined. We'll use a mass flux condition. So pool evaporation rates are typically 0.06 kilograms per meter square per second. And we'll bring it in at 350 Kelvin. Okay, that sets up the flow. Remember, there's a ground surface there, so it won't come in everywhere. It'll only come in through the hole. Now we're going to add the species boundary condition at Z min so that it's coming in as dodecane vapor. It's species and mass fraction. So this will be 1 and all the others will be 0. Okay, so now we have dodecane vapor coming in at the Z min boundary. And that covers it for boundary conditions. Okay, now the next step is to create a mesh. So I'll click on mesh, and we have to do it in all three directions, X, Y, and Z. This was the default that it came in with, but the best way to do it is to allow the code to scan the geometry and find points that are relevant that you want to map to. So now that we know where to insert points in our meshing, we'll go into mesh. We'll scan the geometry like always. We'll use 50 points. Okay, so it's got a mesh there, but we want to insert -5 in here. Well, it's got -6. Which perhaps is okay. So I think we'll leave that. We'll just use that negative direction power law. We're going to use, say, 14, not 14, 5. Yeah, that comes out pretty close. This is the dx that you get based upon these dimensions and these number of cells. And in the positive x direction, we'll use a positive growing power law, and we'll just use 12 here. Okay, now we'll go to the y-axis. We'll do the same thing, scan the geometry. Remember, it does not scan the STL geometry, just the C3d solid modeler geometry. So I'll put in 50 here. And we'd like to have a point at -8. All right, so we need to add a point. Let's call it -8. -8. So you can see it, put that in there. And now we can use -12. Whoops, not -12. Let's use 14. And this would be a negative direction power law. Let's use 8 here, 2 here. And this is the beginning of the hole, 11. Let's make that 13 here. Make this 1. I'm trying to get these dimensions to be about the same. Oh, this would be a positive direction power law. Might want a couple more here. Let's use 15. No, too many. 12. That's probably a fairly good combination. And the z-axis, I think this is probably okay as is, but I'm going to scan it anyway. Put in 40, 39, and positive direction power law here. So it gets stretched in the vertical. Okay. Save that data. Okay, now the next thing we want to do is to map the skin of the airplane to a subgrid so that we can have it heat up and melt out. We'll call this skin. Also call this skin. The reason you enter a name here is because you may have multiple parts in a subgrid, but we're only going to have one. Now the length, I'm not an expert in aircraft building, but I'm assuming that a jet aircraft has a length of 5 millimeters, so we'll put in 005. Number of cells, let's do 2. It's going to be aluminum and very little gradient. If you wanted to track the gradient, you could put in more cells here, but 2 should do it. We have to give it some fluid just to make sure it'll run. We don't want it dividing by 0. And we're going to make it aluminum, auto coupling, and we can search. Yeah, we can search the entire domain for insulator. Remember, we built the ground out of aluminum, and that's why we wanted to pick a different material. Otherwise, it would map the ground as well. And we want to search the entire domain. Here we want to use the default boundary conditions. So we just double click and click OK. And that gives you adiabatic no-flow boundary conditions. It still allows radiation because radiation is controlled by the emissivity of the surface. And that pretty much does it. Click on OK. Okay, we might want to make a little bit of a change to output. These contour slices go through 0, 0, which is somewhere in the middle of the aircraft, except for the Z center. I want that to be not mid position, but a max projection. Full domain, yes. We want it to be a max projection so we can see the pool and the flame looking down from, I think it's up from below. It's in the positive Z direction. We could put in 0, 0 here, but full domain should, I'll put it in just to be safe. If you put in zeros, it means the entire domain. Click on OK. Save data. OK. Now we want to run it. We'll run it for one time step, which is the default. Oh, I forgot to turn off the duplicate polygon checking. I'll do that a little later. Okay, it's all done. Let's actually take a look at the mesh since we did create a variable mesh. You can see the mesh here. It's somewhat fine across the pool. Oh, well, it's too fine here. We needed it to be fine from this location outward. Okay, so there's a mistake in the grid. I'll go back and fix that and get this problem running so that we can see what it looks like. Let me turn off the grid. Yeah, we want, let me check the ruler. So a -6, 0, -6, and then all the way to the y-min boundary. Okay, so I've gone in and fixed the mesh. Now it's fairly fine where the pool is. Let me turn off the grid so you can see the pool. Here's the pool, and it's fairly fine in the region where the flames are going to go. So this thing is ready to run. Now all I need to do is to set up some runtime parameters and let it go. Okay, so we're going to modify the time step. I've already set these to be 5 and 20. Okay, so I'll save that data. Okay, now we'll go ahead and run it. And there's actually an error that I noticed, but I'll show you what it is. And that's the reason I'm running it. It's a boarding calculation, and it says it can't find couple model 1. Check material types and coupling parameters. And the problem has to do with a STL file. We'll go back in here to 1D subgrids, the skin. Okay, the problem is that I tried to couple it to material insulator, which is what I built the STL object with, but it turns out that just because of the way memory is set up, you can't do that with the C3d code. You have to actually couple it to a geometry, and this is airplane.stl. So once you've done that, it ought to work okay. And I wanted to show what that problem was. With STL files, you have to actually couple it to a geometry. Okay, save. Okay, and then we'll run it. And it should go now. Oh, there's a lot of polygons in the airplane surface, as you saw from the pictures. And now what it's doing is it's searching for adjacent polygons so that it can do a little bit of lateral heat transfer. Even though it's very thin, it does take a while. So I'm going to pause it while it does that. It takes a while to get through there. Okay, now it's gotten through that searching, and it's running okay now. So I'm going to pause it and allow it to complete the run to 20 seconds, and I'll show you that result. Okay, so the code has been running for about an hour. It's gotten to, I forgot how many seconds. Let me check. Looks like about 1 second or so. So the fire is still building up. You can say it's coming around the wings, and so on. But I think I'm going to terminate the tutorial here because I've shown how it ends up, and I'll play the actual video that was created from this again one more time just so that you can see how it went. I'm going to close this. So here's the final video that I produced from that run. Recall that there's a wind blowing in this direction from left to right, a pool fire here, and I'll go ahead and play the video. You can see how the wind blows the flames across underneath the aircraft, and we get flames developing. And this first circle takes about 20 seconds. And if you might recall, the emissivity of the skin was 0.1, so the actual time scale for heat up is 10 times longer, so about 200 seconds per rotation. And for the second rotation, the fuel injection from the pool was turned off, and you can see the smoke is dissipating with a little bit of residual flames gathered around the engine, which haven't blown in. And you can see the damage that has resulted. That's a hole that was melted in the fuselage. And this gives an idea of the extent of the damage. Some large hole. This took about a little over 3 minutes. And of course, all of that depends upon what the thickness of the skin is and so on and so forth. And those were all pure estimates in this run, but this gives you an idea of how serious pool fires can be. And that's all I have for this video.